This is problem 58 from Model 1. The driver of an automobile suddenly sees an obstacle blocking his lane. Determine the total distance the car travels between seeing the obstacle and stopping as a function of his reaction time, the initial velocity of the car, and the magnitude of the car's acceleration while stopping. So this problem is similar to the one we just did, but now we are going to include the reaction time. So event 1 would be first sees the obstacle. Event 2 is when the foot reaches the brake. I'm just going to call it presses brake. And event 3 is reaches rest. We're going to start when time is equal to 0. After the reaction time, TR, the brake is pressed, so T2 is equal to TR. And we're given the initial velocity of the car, VI. Let's start at 0. And up until the moment the brake is pressed, the acceleration is 0, which means V2 is the same as V1. And we want to figure out the total distance the car travels between seeing the obstacle and stopping. So this is what we're looking for, and this would be R3. If R1 is equal to 0, R3 is equal to D, and we're trying to find that. Do we know anything else? Well, V3 is equal to 0, and the magnitude of the car's acceleration while stopping is AS, but as we saw in the previous problem, if our initial velocity is positive, then the acceleration, because we're slowing down, is negative. So the magnitude is AS and the sign is negative. We started at 0, so we're going to start here going in the positive direction, and we're going at a constant velocity first. So this is event 1. This is event 2, and then we start slowing down until we reach rest at event 3. Now I can draw my velocity versus time graph, and I have constant velocity, so this is flat up until time 2, which is TR, and then the velocity goes to 0. This is at time 3. And the entire area underneath the graph, so all of this area together, is equal to D. Okay, so I can do two things for the first part of the graph, going between event 1 and event 2. I can look at the slope and the area, but as we saw before, if the slope is 0 and we already know velocity 2 is the same as velocity 1, that looking at the slope isn't going to tell us anything. So let's just look at the area. And since I don't know what R2 is, I'm just going to call that area R2 minus 0. And this is a rectangle if we go from event 1 to event 2, so that's just the base times the height. And so I have the height is VI and the base is TR. Okay, so then I can move on and go from event 2 to event 3. I'm going to look at the area first. And for this part of the graph, we have a triangle, and that is change in position, so that's delta R2, 3, or we could call it R3 minus R2, or since R3 is equal to D, we could say D minus R2 is equal to 1/2. The base is T3 minus TR, that's the distance from here to here, and the height is VI. Okay, and then I know what R2 is, so I'm going to bring this over to the other side. So add R2 to both sides, and then put in this for R2, and you get D is VI TR for R2 plus 1/2 T3 minus TR times VI. And notice we could have written this down all at once. If I know the total area under the curve is D, I could say that's this area, which is this, plus this area under the triangle for the triangle, which is this, and I could have skipped right to that. Okay, so now this equation has a T3 in it. I don't know what T3 is, so I'm going to have to look at the slope to figure that out. Looking at the slope, I know the slope is negative AS. I can clearly see it's negative from the graph. And that is change in velocity, which is 0 minus VI, over change in time, which is T3 minus TR. I could solve this for T3, but actually since what I have in parentheses here is T3 minus TR, I'll just solve for T3 minus TR. So I multiply both sides by T3 minus TR and divide both sides by negative AS. Negative signs cancel out, and I get T3 minus TR is equal to VI over AS. Then I'm take that, put it in for what I have up there. Kind of short on space, so I'll just keep writing it up here. This is VI TR plus 1/2 of T3 minus TR is VI over AS. This is times VI, so let's squeeze it in down here. So D is equal to VI TR plus 1/2 VI squared divided by AS, and that is my final answer. And if I compare this to what I had in problem 57, whoops. Okay, so if I compare this to what I had in problem 57, in problem 57, we could say it's the same thing, but with TR equal to 0. So if TR is equal to 0, I just have 1/2 VI squared over AS, which is the same thing I have there. So that looks promising. Then I can answer the questions at the bottom of the page. So if VI is equal to 0, what should D be equal to? Well, if you're already at rest, you don't have to cover any distance to reach rest, so it should be equal to 0. Does your function agree with this observation if VI is equal to 0? Yes. D is equal to 0. For question 2, if AS is equal to 0, what should D be equal to? So again, if you don't slow down at all, you're not going to stop, so you would cover an infinite distance before you ever stop. Does our function agree? If AS is equal to 0, we're dividing by 0, so yes. And this term would go to infinity, and if you add something to infinity, it would still be going to infinity. And then we're going to skip the last question here. So that concludes problem 58.